Welcome to this video number 4 in the phase equilibrium series. In this video, we will go through the different uh, phase boundaries. For example, we'll go through what happens to a solid liquid boundary, what happens to liquid vapor boundary and solid vapor boundary in a one component system, and we'll see how the curves are. Are they steeper, are they slantier, and compare each with another. We'll also introduce you to Clapeyron equation and also Cauchy's Clapeyron equation. So let us go through their features. So when I say that two phases are in equilibrium, when two phases are in equilibrium, what it means is their Gibbs free energy. See, whenever delta G is 0, only then they are in equilibrium, right? So their Gibbs free energy is 0, and since chemical potential is molar Gibbs free energy, I can also tell that their chemical potential in alpha phase. Suppose I say alpha and beta phase are in equilibrium, so they both should be same. Now, from our Maxwell relations and everything, what we know is delta G is equal to Vd minus SdT. Okay, or if I have to tell you, d mu, that is chemical potential, is molar Gibbs free energy, therefore v molar volume dP minus molar entropy dt for each phase. Okay, in each phase. Now since at equilibrium d mu alpha is equal to d mu beta, chemical potential in phase alpha and phase beta are same, so what I can write is I can tell that Vm alpha dp minus Sm of alpha dt should be equal to Vm beta dp minus Sm of beta dt. So I can take them one side and write Vm beta minus alpha Vm alpha dp is equal to Sm beta minus molar entropy of alpha phase dt, and then I can equate. So what will this give you? dp by dt, if I transpose here, what you will end up getting is Sm beta phase minus Sm alpha and Vm beta phase minus Vm alpha. So this is what? This is the delta change in transition of entropy, and this is your change in transition of volume. So dq by dt. Okay, or if I, so this is called as Clapeyron equation. I think there's a slight spelling mistake here. So it is Clapeyron equation. Okay, so we will see how this is used. So let us take a solid liquid boundary and study in a one component phase diagram what will be the nature of solid liquid boundary. So what is the transition that is happening? Solid to liquid. Okay, so or liquid to solid, both of them are represented by a single curve. So melting is accompanied by molar enthalpy change, or let me make it more simpler. See, your delta S is given by Q by T, Q reversible by T, right? Okay, now what is Q reversible by T? It can be given by delta H by T of certain, of not be T, and the transition that is happening. Okay, so if here melting is also accompanied by molar enthalpy change, and since it is solid to liquid, I can as well write delta S in terms of delta fusion. Okay, your dP by dt, which is given by delta S transition entropy divided by delta transition volume. I can write it as delta fusion enthalpy divided by T and delta transition volume. Now delta H fusion is positive value. It is mostly positive value, and delta V is also positive value, but very small. Why? Because solid is becoming liquid and the volume difference is very small. See, it is not as bigger as when liquid becomes gas, right? It just occupies the whole room, but that is not going to happen. Solid to liquid volume difference is very small, and because this is small, what happens is this ratio becomes very big. So big number. What this tells us is, because this is denominator is very small, the entire number is big. So what this means is slope dp by dt is very steep and usually positive. So it's very steep. That is why on a phase diagram between in dp by dt here, the solid liquid curves are very steep. Solid liquid curves are very steep. Now let us see for what happens for a liquid vapor pressure, liquid vapor boundary. So the entropy of vaporization at a temperature T is equal to and therefore your dP by dt, which is delta transition S by delta transition volume, is given by delta vaporization temperature to delta vaporization volume. Now what happens is, this is a positive value, this is also a positive value, this is a large and positive value. So therefore your slope dP by dt is positive, but much less, because there is a large value in the denominator. This value, entire value, is much less steeper than for solid liquid boundary. So your curves on a pressure volume graph, pressure temperature graph, for solid liquid it was very steep, but for liquid vapor it will be much slantier. So liquid vapor. Okay, let us see for a solid vapor curve. Third, so again same thing, the entropy of sublimation at a temperature T is given by delta sublimation enthalpy divided by T, and your dP by dt. So obviously this is also a positive value, this is also a positive value and much larger. Therefore the slope is positive, but much smaller than solid liquid boundary. Okay, but now if I have to compare solid vapor and liquid vapor boundary, what happens is, delta sublimation of enthalpy is greater than delta vaporization enthalpy. So solid vapor boundary, that is sublimation curve, is much steeper than liquid vapor curve. Liquid vapor boundary. Okay, so if I were to rank the steepness, the steepness of curves, first from highest to lowest, it would be solid liquid boundary greater than solid vapor boundary greater than liquid vapor boundary. So this will be your steepness of the curve. So thank you.